What are they? A rational function is a function that is a quotient of two polynomial functions, such as f of x equals a of x over b of x, where b of x cannot equal 0. Examples include these three, and there are many graphs that could result, such as these. Intercepts. Intercepts are points where the graph crosses either the x-axis or the y-axis. In this example, the intercepts are about 2.50 and 0, negative 1.5. Let's do an example. F of x equals 3x squared minus 3 over x squared minus 9. The y-axis intercept is when x equals 0, so we'll plug in 0 into x. We solve and y equals 1/3. Therefore, the y-intercept is 0 1/3. For the x-axis intercept, we're plugging in 0 into y. To solve, we find out that x equals plus or minus 1. Therefore, the intercepts are 1, 0 and negative 1, 0. For another example, 8 over x squared minus 4. The y-axis intercept, as we work out, is 0, negative 2. The x-axis intercept, we solve and see that 0 does not equal 8, therefore there is none.
Next, we will be talking about symmetry. Symmetry in graphs can appear in two different ways. The graph can be folded along a line symmetry, or it can be rotated 180 degrees with respect to a point and remain unchanged, point symmetry. The most common types of symmetry are x-axis symmetry, y-axis symmetry, and symmetry with respect to origin. X-axis symmetry occurs if every y is replaced with a negative y, and then an equivalent equation is produced. Y-axis symmetry occurs if every x is replaced with a negative x, and an equivalent equation is produced. Symmetry with respect to the origin occurs if every x is replaced with a negative x, and every y is replaced with a negative y, and an equivalent equation is produced. Graphs of rational functions can only have two types of symmetry: symmetry with respect to the origin, or y-axis symmetry. If the graph has x-axis symmetry, then the equation of the graph is not a function, because the graph does not pass the vertical line test. If a graph does not pass the vertical line test, it shows that the graph does not represent y as a function of x. Knowing the symmetry of a function can make it easier to graph the function. If you know the symmetry of the graph and a point on the graph, you automatically know another point. This way, you only need to find one point on one side of the graph to find a point reflected over the axis of symmetry. These graphs show y-axis symmetry and symmetry with respect to the origin, which show that these graphs represent a rational function. This graph shows symmetry, x-axis symmetry, which shows that the graph does not represent a function. Now we'll be talking about holes. Holes appear on a graph when the numerator and denominator of a rational function have common factors. The hole occurs at the value of which the factor is equal to 0. The function here has a hole. After factoring the numerator and denominator, you can see that both numerator and denominator have a common factor of x plus 1. After canceling x plus 1 from both the numerator and denominator, the equation left is x plus 2 times x plus 3, also known as x squared plus 5x plus 6. This function shows that there is a hole occurring at x equals negative 1 because that is a common factor between both the numerator and denominator. The graph of the function looks like this. The hole occurs at point x equals negative 1 on the graph, and the common factor for both the numerator and denominator in this rational function is x plus 1. When x plus 1 is set equal to 0, the x value is negative 1. At this point, a hole appears on the graph.
Now we will be looking at asymptotes. What is an asymptote? An asymptote is a curve or line that the graph approaches. There are two types of asymptotes: vertical asymptotes and end-behavior asymptotes. The end-behavior asymptotes we will be discussing are horizontal and oblique asymptotes. Vertical asymptotes. To find the vertical asymptotes, find the zeros of the denominator of the function and set them equal to x. The function can never cross a vertical asymptote. This is because at a vertical asymptote, you are dividing by 0, so the function can never be defined at this asymptote. Make sure the zeros of the denominator are not the zeros of the numerator when you're finding this asymptote. If this is the case, the two factors will cancel out, and you will have found a whole, not an asymptote. Let's look at f of x equals 1 over x minus 3. To find the vertical asymptote, set the denominator equal to 0. When you solve, you see that the vertical asymptote is x equals 3. If you look at the graph of this function, you'll notice that it is approaching this line x equals 3, making it the vertical asymptote. Now let's look at end behavior asymptotes. End behavior asymptotes, as you can probably guess, are asymptotes that define the end behavior of a function. There are two types that we will be discussing, horizontal and oblique. Horizontal asymptotes. Horizontal asymptotes can be found by observing the relationship of the degree of the numerator and the denominator. If the degree of the numerator is greater than the degree of the denominator, then a horizontal asymptote does not exist. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. If the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is y equals the ratio of the leading coefficient of the numerator to the leading coefficient of the denominator. The function can cross a horizontal asymptote in what are known as crossing points. To find the crossing point, divide the numerator by the denominator, set the remainder equal to 0, and then solve. Now let's look at y equals x cubed over x plus 5. The degree of the numerator is 3 and the degree of the denominator is 1, so the degree of the numerator is greater than the degree of the denominator. This means that there is no horizontal asymptote. If you look at the graph of this function, you'll notice that it is approaching no one horizontal line. Now let's look at y equals x plus 5 over x to the 4th. In this case, the degree of the numerator is less than the degree of the denominator. This means that the horizontal asymptote is y equals 0. If you look at the graph of this function, you'll notice that it is approaching that very line. To find the crossing point for this function, you can set the remainder equal to 0. X plus 5 divided by x to the 4th has a remainder of x plus 5. When you set that equal to 0 and subsequently solve, you'll notice that you get x equals negative 5. This means that the crossing point is negative 5, 0. This is where the function will cross the horizontal asymptote. Now let's look at y equals 9x squared over 3x squared plus 1. In this case, the degree of the numerator and denominator are equal, so we have to find the ratio of the leading coefficients. The leading coefficient of the numerator is 9, and the leading coefficient of the denominator is 3. 9 divided by 3 is 3, meaning that the horizontal asymptote is y equals 3. If you look at the graph of this function, you'll notice that it is approaching that line. To find the crossing point, you would do the long division, and you would see that the remainder is negative 3. This means that there is no crossing point, because negative 3 will never equal 0 under any circumstances. Oblique asymptotes. Oblique asymptotes occur when the degree of the numerator is higher than the degree of the denominator by 1, exactly 1. They're found by dividing the numerator by the denominator. In your asymptotic equation, do not include the remainder. Only include the quotient without the remainder. The function can cross an oblique asymptote in, again, what are known as crossing points. These crossing points are found in the same way you find the crossing points for horizontal asymptotes. Let's look at y equals x squared over x minus 3. To find the oblique asymptote, divide the numerator by the denominator. You get x plus 3 as a quotient, excluding the remainder, so the oblique asymptote is y equals x plus 3. If you look at the graph of this function, you'll notice that it is approaching this line. The remainder of this long division is 9. 9 can never equal 0 under any circumstances, meaning that there is no crossing point for this asymptote.
The function we're going to graph today is x cubed minus x squared minus 2x all over x squared minus 1. When we factor it, we get x times x minus 2 times x plus 1 all over x plus 1 times x minus 1. Then we cross out the x plus 1 on both the numerator and the denominator, and we get left with x times x minus 2 over x minus 1. To find the x-intercept, we set the function equal to 0. And then we get 0, 0, and 2, 0 as our x-intercepts. To find the y-intercept, we substitute in 0 as x, and we solve. Then we get 0, 2 as our y-intercept. To solve for the vertical asymptote, we set the denominator, which is x minus 1 equal to 0, and we're left with x equals 1 as our vertical asymptote. The horizontal asymptote, or the EBA, is found by dividing the numerator by the denominator because it has a degree one more than the denominator. So x squared minus 2x, and you divide it by x minus 1, and you get x squared minus. As a result, we get x minus 1 as our horizontal asymptote. So y equals x minus 1 is our horizontal asymptote. And because the remainder is negative 1, and it's not equal to 0, we have no crossing points. Now let's graph this. Vertical asymptote. Now we're going to graph a few additional points. Then we connect the dots. Now we are left with this as our graph. We hope you enjoyed our video, and we hope you learned a lot from it. Thank you for watching.